Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson, and we're going to be talking about an acronym, a three-letter acronym, which is always a good thing, the MLE.
The MLE. Well, it came out as a short discussion, I should say, through LinkedIn, one of the many ways you can get in touch with us. But it started with, well, what's wrong with the software defaults? And it was relating to a data analysis, a reliability data analysis package that gives you options of how you do the analysis for how you curve fit or do the regression or stuff like that. And this particular package has, now I'm drawing a blank on it. It's maximum likelihood estimate, MLE, is one of the options, but it's not the default. The default is rank regression. And I think they call it X rank regression, and then there's another one called Y rank regression, which I never understood why anybody would use that. But I guess there's cases where you would, but I have never found one. I said, well, what are you trying to do? And he said, well, I'm trying to fit some field data, and we've got lots of sensor data and not a whole lot of failures and stuff like that. Or it was like a situation where I would just say, oh, you need to use MLE. And they says, well, the response back was, well, I don't know what that is. So I'm not going to use it. And it put me on my heels a little bit. And then what the hell are you doing analysis? And I've run into it before where somebody will open up a package and try all the options, find the one they like the most, and print it. And the one they like the most is closest to what the answer is they think it should be or their boss would like, independent of whether it's a reasonable analysis at all. And I was like, there's a problem here. Sorry.
Yeah, I think that rank regression on Y is depending on which Weibull analysis master's book you read gives you a better fit of a certain reliability data. But again, you're still talking about the line of best fit. None of these rank regression on X, rank regression on Y, MLE, there's a couple of others as well. None of them are all about. None of them of themselves deal with confidence and confidence intervals on that line of best fit. And, there's also lines where, especially for Weibull, which are attempts to remove biases. So you have a bit more of an equation which someone's come up with to hopefully, sort of remove any inherent inaccuracies you have. But again, the other thing too is that you're talking about usually when it comes to Weibull analysis, rank regression on Y or rank regression on X. They're also based on where those data points you plot are on the Weibull plot. So you have to estimate the CDF for each data point, and that dot you draw, that then becomes the dot you use to sort of get your rank regression on X and rank regression on Y sorted out. One of the problems with that, though, is that the actual physical distance on a Weibull plot is exacerbated or counts are a whole lot more at the top right and bottom left-hand corners. So in a way, it sort of fine-tunes, more focused on the first few failures and the last few failures have an undue influence on the line of best fit. And rank regression is quite literally trying to find a line where it sort of minimizes the distance between the line you settle upon and the data points as plotted. So you minimize the distances between those data points and your line of best fit. Rank regression on X those distances are based on vertical distances, and the rank regression on Y, those distances are based on horizontal distances.
And it's not too dissimilar from just getting a piece of graph paper and plotting the dots and then drawing a line through it, like the old Weibull probability plotting paper. And you're actually, and I tried it way back when I first had a computer to do the regression for me, and it was pretty darn close by hand.
Yep.
It's it's not an algorithm that's too dissimilar to what we do, saying, well, what's a line that is the closest to all the points on here? What do I? And the computer just does it mathematically and says, all right, we'll tweak it just a little bit here or there, and there you go. That's a good spot. I can understand that, and I think anybody that's had a regression at class is like, that's usually pretty simply taught. And I think it's more advanced uh, uh, education gets you into what is an MLE and why and when would you use it and what advantages and disadvantages. But it speaks to the basic problem I find is that you can buy a software package for $1,000 or whatever they run for these days and stick a bunch of data in it and push buttons. And it's not too dissimilar when calculators came out. And one of the guys in my class had the first graphing calculator in the class. And he came up with just physically impossible curves to explain things. It's like we were in a chemistry class and he had negative activation energies or he had curves showing that, time started about 3 days ago. I mean, just do you even check where your fingers are when you're pushing the buttons on this thing? And it was just well, I don't need to think. I'll just use a computer. And I think that's what really upset me about, or not upset me. It was like concerns me about the software packages and how people go about using them these days. And MLE is, you should understand enough about when and why you would use it and what is it doing. It's a good thing to do, yet there's so many other options on the software packages these days that, you might need an advanced degree in statistics to really understand it. The software package vendors are saying, well, we already thought this through for you, so you don't. And I've had long discussions with some of these folks going, well, then why don't you add the hints and tips and guidance to say, this is when you should use this algorithm. Don't pay attention to this goodness of fit criteria, or make sure you check these 6 assumptions if you're using this curve, those kinds of things. And they said, nah, customers don't want to be told what to do. Okay.
Well, I think they're right. I mean, unfortunately, customers just want to have numbers in, make this reliability stuff go away. That's a thing.
Yeah.
It's a prevalent. But the reality is that's only if you work in an organization where you're not invested in the outcomes. You just want to be able to say, I've done the work and go home. Plenty of organizations where the employees are way more empowered to go and solve problems and are expected to go solve problems. They're the ones who say, let's hold up. I want to know a little bit more about this thing going on before I sign my career away. And they're the ones who are much better to talk to. Let's just say that.
Yeah. So it's a fair question. I don't want to use it because I don't know what it is. At least they took that step. They didn't try all 3 different regression techniques to figure out which one gave them the air quotes here, right answer, independent of the analysis. I give credit to somebody that actually says, I want to check, and make sure what's going on. Yet I've also run into people that have a advanced degree in statistics and are doing an analysis of, say, an accelerated life test, and they come up with absolutely impossible results. They did the statistics right, for example, yet I think there's a disconnect between, we got an activation energy of 427 electron volts, not decimals at all, or not, no reality check as to what it is. They just kind of use the Arrhenius equation as a random fit and use the activation energy as a parameter. And no second guessing, no checking, no comprehension of, that value is just not physically possible, I don't think. I'd have to check with the chemist, but at least the question said, well, I'm not sure what that is, so I'm leery of using it. That's a good thing. And if it's followed up by going out and check, reading about it or studying it or asking some questions. That's all fine. It's the ones that turn the crank and ignore the reality, the gut check or the reality check that comes with doing an analysis. Yeah, there was one that I ran into where they were using I can check like 12 different distributions. And so every week they got the next week's worth of field data. And they did two things that I thought was just odd. One is they ignored all sensor data. They just plotted charts with just the failure data. So it would always go to 100% or 99%. It would go from 1% to 99%. And every week, this was the same product and the same basic dominant failure mechanisms that were occurring in their product. And every week they checked all the possible fits, and they use gamma, they use, the Uber gamma, they use the Weibull 3 parameter with a negative, with time to failure before it was produced. That was the group that I ran into that one on. And every week it was, I kind of have a random choice of what distribution to use. I'm like, that somebody somewhere should have said, that just doesn't make sense. And that's the part I think is missing too often.
I often come across students when I teach my courses, I try and minimize the equations for like the discussions on statistics. So the bell curves, log normal distributions, everything else like that. But sometimes, so for example, I ask a student body, all right, so this is how the failure is occurring. It's wearing things. We understand the physics of how this thing wears out. It's losing, let's just say, tread for a brake pad, for example. It's losing roughly, on average, the same amount of tread per kilometre on average. So what sort of distribution should that be to describe time to failure? And the answer is, we've done lots of other podcasts and webinars on the topic. It's a bell curve. When you have things adding up, like the amount of cumulative brake pad material that's worn away over time, that adds up in a very uniform way. The amount of brake pad material you expect to lose in the first 10 kilometers is the same as the amount of brake pad wear you expect to lose in the next 10 kilometers and the next 10 kilometers after that. Classic adding of multiple random processes, classic textbook application for the bell curve. But I still have students say, but how do you know that's true? How do you prove that that's true? What do you mean, how do you prove that's true? If you understand how things fail, it's not about proof. It's about understanding how it fails. But how do you know it's true? And essentially, they're not happy until you have 600 data points with a p-value which is suitably good enough to say, okay, that's now a bell curve fit. No, that's one of the problems I also come across, where we say confidence is a measure of you, not a measure of your system. If you have zero confidence in your, and I don't say this to the students, but what I in practice, I suppose, should be saying is, if you don't have any confidence in your ability to understand how this thing fails, why should I have confidence in you as an engineer? If you have to have it proven to you by numbers and data points before your expert judgment is going to come into play, then you don't have expert judgment. You don't want to be that reliability engineer. And that happens too often, I would argue.
Yeah, no, I agree. It's part of it is, and I got a request for a project the other day, and there was this, well, how do you go about doing warranty analysis? Well, what are you trying to do with the results of the analysis? And the other part is, what's the failure mechanisms that are driving the warranty stuff, and how many are there, and how different are they? And the response was, well, you don't need that stuff for your doing it. And like, well, then I guess my analysis will not be helpful for you if you just want to ignore physics and science and chemistry and the engineering part of this thing. If you want somebody to just crank out a Weibull plot for you, you can go hire somebody a whole lot different than me to do it.
I do find it amazing when you get hit by these companies and organizations who have clearly hit some sort of roadblock, and they don't have the ability to get the answer they need. And say, okay, I'll reach out to, people like you or people like me and say, okay, no worries. Can I have the rest of the information? And all of a sudden they become experts again and say, well, you don't need that. You don't need that information. You don't need this. You need to do it this way. And I go, didn't you guys call us or call me
Yeah.
to get on top of this? No. All right.
Yeah.
Well, best of
No,
luck, Div.
there's an advantage of saying, I can see that this is not going to be helpful for you, so I'm not going to waste your time. So
Yeah.
find somebody that's willing to do whatever you want them to do and get a random answer, and then you'll be happily trucking along until it doesn't actually solve anything.
Right.
Good luck with that. The advantage
Yeah.
of being very selective of who I work with is I can tell them to go take a leap, take a short walk on a short pier, a long walk on a short pier or something like that. And I'm like, no, I don't think I can help you with this.
Yes, you're unhelpable. And there's plenty of those.
Yeah.
If I find it the dichotomy very hard to deal with where, you're not expert enough to solve this yourself, which is why you're reaching out, but now you're expert enough to tell me that this is how it's going to happen. All right. Pick one.
Yeah. Well, anyway, so I guess we should actually include a note on, well, what is MLE, maximum likelihood estimate? And I figured you would have a nice short, 150 word description of it, maybe.
Well, it's just that for any probability distribution, like imagine any curve, bell curve, or something similar. If you've got a number of data points, you can come up with a number which represents the likelihood of that curve representing those data points, or describing the random process which gave rise to those data points.
So physically, I have like a scatter of points on a chart where, and then I draw a line in it and go, well, this one's the most likely curve or the most probable curve to, if I would random sample from it, I would get those points, kind of thing, or something very similar to it.
Well, let's just say you have a bell curve as one candidate probability density curve, and let's just say an exponential distribution curve as another candidate PDF or model. And you got to say, just choose between those two. Well, you can ask a computer to say, all right, all you need to do is essentially plot those data points on a chart, draw the candidate bell curve or what have you over the top, draw lines up from each data point to the bell curve, and multiply the heights of those lines. So that process is just how a computer would go about coming up with a likelihood number for candidate.
And then they would try a whole pile of different curves, variations of the normal curve to say, oh, it's got a mean of this and a standard deviation of this. And that's the one that minimizes those discrepancies. But it includes information about all the points and the sensor data, which is a little more complicated, but it counts the stuff you don't plot.
Which makes MLE a lot more powerful, I'd argue, than regression, especially if you have censored data. Yep. Because MLE is it's just so much more robust at taking into consideration those data points. You don't have to worry about where that data is plotted on a CDF chart, which involves estimating where the CDF is, or rank regression does. Sorry, regression.
Rank regression.
On X. On X, rank regression on Y, you do. And lots of others, root mean square, for example. And so for that reason, I think it's a lot more robust. The issue that some might say is, well, it becomes the most likely. It's not the mean or the median line of best fit, which is true. But again, what question are you trying to answer? I would argue that the line of best fit is not nearly as important as the confidence interval on the line of best fit. That confidence interval is way more important in my perspective than the line of best fit. You might have a slight change if you use MLE versus regression on X or regression on Y or anything else, but it's a region within which you are confident the true line lies, which sort of contains a lot more information, at least for me, when I want to make some decisions. But that was a little bit more than 200 words. I don't know.
I
run with it.
I'll go with it. Yeah. So anyway, it's one of those things that if you've got a question like that, if you're like, why is it doing this, or how do I use this option, or, what's a way to approach this problem? It's got to be different than just plugging numbers in a calculator kind of thing. We'd love to hear that. Is, what's hanging you up? What, piece of it can we help you move past that and have more confidence, personal confidence in that you're doing the right thing. And we'll ask maybe embarrassing questions like, have you checked the assumptions? What kind of data is this? What's the physics going on here? Things like that. It's and then what are you trying to accomplish? Is this a comparison? Is it a monitoring for problems? Is it, there's dozens of reasons why we do different analysis. And so that's part of it. If you're not sure what you're trying to achieve, well, then I guess anything you come up with will be just fine. but let us know. Head over to accendoreliability.com/go/SOR. There's a couple of ways to get in touch with us there. LinkedIn recently has been the most popular, and Chris and I and the other hosts of the show are available on LinkedIn to pick up your questions and have a discussion about what's going on. And also you can find our contact information in a variety of places, but including our about pages on Accendo Reliability. So plenty of ways to help you answer some questions or, scratch your curiosity or something like that and figure out how to move forward. We'd love to help if we can. And it also makes good fodder for podcast episodes. So we always look forward to that kind of stuff.
Okay.
All right. Well, thanks, Chris. We'll talk to you again soon, I'm sure.
Always a pleasure, friend.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.